Alright, so we're going to talk about properties and attributes of polygons. We've talked about triangles, we've talked about quadrilaterals. We want to talk about polygons in general. So I saved some data. Alright, so we're going to be talking about classifying different polygons. Remember how we classify different triangles, right? By sides and by angles. We're going to be classifying polygons, and we're going to be talking about interior and exterior angles. You guys are familiar with those a little bit, but we'll talk about what they look like on polygon. Here's a definition of a polygon. A polygon is a closed plane figure formed by 3 or more segments. So it's important that it is closed plane figure that has 3 or more segments, and they intersect only at their endpoints. Meaning, while triangle is a polygon and quadrilateral is a polygon, and even octagon, let's see if I can draw this, octagon is, because they are closed, they have 3 or more segments, right, 3 or more, and they intersect only at their endpoints. These are some of the polygons these are some of the shapes, bless you, that you might think are polygons, but not. Circle is not a polygon. Some weird shape like that is not a polygon. While it is closed, the segments are not intersecting at their endpoints, and even the moon, it's not segments, right? Those are kind of curvy lines. These are not segments, so those are not polygons. But believe it or not, star is a polygon. It's closed, they only intersect their endpoints, and there are 10 segments, which is definitely more than 3. Here are different names for polygons. What's the name of the polygon when there are 3 sides? Triangle.
Trilateral.
Right? Trilateral just sounds so much more sophisticated. I don't know why we don't use it. I'd be totally okay with that. But then quadrilateral does get its sophisticated and complicated name, just for a 4-sided polygon. 5-sided polygon is called pentagon. 6-sided polygon? Hexagon. Ooh, this is gonna get some of us. 7-sided polygon. Just yell it out. Yell it out. I hear septagon. Heptagon. Why did you get heptagon? It is called heptagon. Yes. Yes. If it has 8 sides, Tommy, do you remember what the polygon is called?
Octagon.
Yes, octagon. Ian? 9? Do you remember? Do you know this?
Oh, I know.
Nonagon. Yes.
Decagon.
Decagon.
Dodecagon.
Yes, dodecagon. Dodecagon is a polygon with 12 sides.
Oh, dodecahedron is like a 3D.
Yes, yes.
Yeah, exactly.
Wait, what's the time to say?
They're called polyhedrons. So tetrahedron is a 3D shape with 4 triangles.
Wait, what is 10? Diagon?
Decagon. Oh, sorry, decagon.
Oh.
Decagon, and dodecagon is a polygon with 12 sides. You might be thinking, why did you skip 11? Because you don't really hear 11-sided polygon as much, but it is called, yes. I think it's on decagon. On decagon. Now, whether it has 12 sides, 13 sides, or 100 sides, as long as it's a polygon, we can say it's an n-gon with n number of sides. So technically you can say 10 gone. Technically you can say 9 gone. Technically you can say 17 gone. It just means that it's a polygon that has that many sides.
Since you've been gone.
What's that?
Nothing, it's a music reference.
Okay.
Since you've been gone.
Funny, CJ.
That's kind of funny, actually.
You're hilarious.
If you were in a different setting, I would have laughed out loud. Very loud. Isaiah, is the first figure on the screen polygon?
Yes.
Yes. Why? What is it called?
It's called hexagon.
Hexagon. Yes. It's called a hexagon. It has 6 sides. What about the second one? Aiden?
No,
No. Why not?
because that's one of the ones you said wasn't.
Sure.
Oh.
Why not? Why did we say it's not, Jonathan?
It has curved lines.
Yes, it's got curved lines, and it is. So that means it's not segments, right?
Yes.
And if you call those segments, I guess in some sense you can, if you look at it, if you work in a spherical geometry. Oh, so cool.
Is it because it only has 2 segments?
Yes, it needs 3 segments. 3 segments. And segments are straight too. Yes.
Another question.
Mm-hmm.
I'd like to draw it.
Sure.
Alright. Would this be a polygon?
You're gonna draw a boat.
Huh?
Never mind.
What?
Someone in a different class drew something else. Anyway, go ahead. So.
You should put this on the slide.
Right. So something like this is not a polygon.
That's a piece of
So it's
toast.
like a loaf of bread.
Oh wow. Oh no. What have I done? What have I done? Ah, never mind. Yes. Loaf of bread. No, that won't be a polygon.
Piece of toast.
It needs to be all the lines that make up
No, so
the
no.
polygon has to
So
be
even if there's 3
straight.
segments that are the round sides.
Right. So like something like this.
Yeah.
Yeah. No, those won't be polygons.
Wizard hat.
The wizard hat. Sure. What about the third figure here? Zach, is that a polygon?
No,
Why not?
it's endpoint on
Yes, it's not closed. Good. This one's. All right. What about the last one? Robbie, is that last one? You said it was. Yes.
Said yes.
If you were to say that's a polygon, what is it?
Octagon.
Octagon. Yes.
It looks like those things in Star Wars.
TIE fighter.
Yeah.
Oh.
Oh, I see.
Oh yeah, I can see that. Or a bow tie.
Yeah. I was thinking bow
That also doesn't look very handy.
Alright, a regular polygon that we say is both equilateral and equiangular. Now, if it's equilateral and equiangular, that might seem synonymous for us because remember how equilateral triangle was always equiangular? If you imagine a regular quadrilateral, it would be a square. It's equiangular and equilateral. And you can even picture a hexagon that's equiangular and equilateral. But we need to make sure we don't make the mistake of saying that equilateral just means equiangular in general. Yes, it is true for triangles, but it may not be true for other polygons. Can you think of a shape that is equilateral but not equiangular? Equilateral but not equiangular. CJ?
Rhombus.
Rhombus? This is a rhombus.
Kite, I'm sorry. Actually, well, some
A diamond.
rhombus, yeah, diamond.
Sure. So a rhombus that looks
They get
like this, right? A rhombus that looks like this, where because it's a rhombus, it's got 4 congruent sides, but the angles aren't all congruent. This is equilateral, but not equiangular. What about shapes that are equiangular, but not equilateral? George? A rectangle, yes. A rectangle, which has 4 right angles. All the angles are congruent, but the sides are not. Good job, guys. That was quicker than I have experienced. Now, remember how we said a star is a polygon as well? It's called a concave polygon. In fact, it's a concave decagon because it has 10 sides. You can kind of simply think about concave as a shape that's kind of caved in, right? So if you look at the left, concave quadrilateral here is caved in, right? And on the right is convex. Convex polygons are typically what you think about as polygons, those kind of like round ones. The official definition is that a polygon is concave if any part of a diagonal just connects two vertices, contains points in the exterior of the polygon. So do you see how when we connect these 2 vertices, the diagonal is outside of the polygon? If that happens for any of the diagonals, then it's concave. For convex quadrilateral on the right, all the diagonals are inside the polygon. They don't touch the outside. Therefore, it's convex. So if you think about, say, a star, right? While these diagonals are inside, this diagonal is on the exterior of the polygon, which means that this is a concave decagon. Whereas if you had a regular hexagon where all the diagrams,
There's no undo button.
I don't know how that works.
Wow.
I'll figure it out. I think that's undo, but I don't know. Anyway, all the diagonals stay inside, right?
You can make a star with those.
Yes, you
You
can.
just did make a star.
Then it's a convex polygon. So let's name these figures. Can someone name the first polygon? What would you name that as? You need to either say it's regular or irregular or concave or convex, and try to name it depending on the size, number of sides it has. Aiden?
It's a regular convex hexagon.
Yes, it's regular because it's equilateral and equiangular. It's convex because all the diagonals stay inside, and it's hexagon. Oh, and you want to give the next one a try?
Yeah, concave regular.
Concave, regular? Why do you say regular?
Because only. Oh no, it's irregular.
Why do you say irregular?
Because none of the sides are congruent.
Right. Some sides are congruent, but not all of them, right? So it's irregular. What would you say? What gon is it?
What?
How many sides are there?
Too big. Eight.
There is more.
If you count one side, you will multiply by 2.
Split it into like
12.
12 is a dodecagon. Oh, shoot. It's a It's weird, I can't erase it. Why not? Dodecagon. The last one?
I just have a question. What's
Oh,
the
yes.
difference between
Regular, irregular.
Regular is equilateral and equiangular, meaning all the sides and angles are congruent. Well, all the sides are congruent and all the angles are congruent. Here, while all the angles are congruent, they're all right angles. They're not all the sides are congruent. That's why it's irregular. Sure.
It's an irregular convex rhombus.
Convex. Be more general. Like how many sides it has? Does it have? Quadrilateral. Yeah. You just say convex. Good stuff. Questions on this page? Well, let's name these really quickly. We have triangles, and we have quadrilateral, pentagon, hexagon, and n-gon. Speaking of n-gon, let me pitch something a little philosophical to you guys. What do you notice as the number of sides increases?
It gets more circular.
It gets more circular. So can you imagine if you had, say, 100 gon or 1,000 gon or even 1,000,000 gon? It would look more and more and more circular.
If it's regular.
If it's regular and if it's concave.
Yeah.
So circle, in some sense, not technically, but in some sense you can say, is the infinity gon. Maybe? Just think about it, right? And there's something really cool that relates to that later on when we talk about types of angles. But I'm not going to spoil it for you. Anyway, circles can be considered maybe, as infinite gon because it has infinite number of segments, but really infinite number of points around it. And if you connect all those points together, the diagonals will all be inside, so it's really convex, regular, infinity gon. Anyway, just wanted to pitch that there. Yes?
Aren't there limited number of triangles in all of these? Because within the triangles you can make more triangles.
Kind of. Let me explain what this means. Clearly, there's only one triangle that you can make out of a triangle, but let's take a look at quadrilateral. Here, we have a quadrilateral here. You already know that the sum of interior angle measures for a quadrilateral is 360, right? Yes, 360, and we know that it's 180 degrees for a triangle. But here's a really neat way to look at the sum of the interior angle measures within a quadrilateral. Check this out. If I were to cut this quadrilateral into two triangles, the sum of the angle measures of the red angles over there is 180, right? And the sum of the angle measures for the blue angles from the triangle on the right is 180, right? What happens is that all the interior angles are composed of the interior angles of those two triangles. And since the sum of the interior angle measures of each triangle is 180, so it's 180 altogether between the three of here, and 180 between the three here, the sum of the angles, interior angle measures, is 360. Because there are two triangles whose interior angles cover the interior angles of a quadrilateral. We can also apply the same concept with pentagons. if you were to split the pentagon into 3 triangles so that all the interior angles of the triangle cover the interior angle measures of the pentagon itself, isn't that really 180 times 3? Because there are 3 triangles that cover all the interior angles of the pentagon. So since there are 3 triangles, 180 times 3 is 540. That is how many degrees? If you were to combine all the interior angle measures, that's 540 is how many degrees will be there. Try to guess how many triangles you can form with hexagons so that all the interior angles of the triangles cover the interior angles of this hexagon. George?
Is it 4 triangles?
It is 4 triangles. And you can see that if you have a hexagon, we can split up the hexagon into 4 triangles so that the interior angles of the triangles can cover the interior angles of a hexagon. Can you see that? Since there are 4 triangles, yes?
Is the sum of the interior angle measures the sides minus?
Oh, whoa. Wait a second. You're jumping ahead. People are thinking about the sum of the interior angle measures. I'm going to come back to you, okay, Owen? I'll come back to you. But what is the sum of the interior angle measures for hexagon? 720. That's because there are 4 triangles that are in the hexagon, or any hexagon. It doesn't mean that you have to split up just like that. You can even split it up like this, right? Still, the interior angle measures of the triangles cover the interior angle measures of the hexagon. So Owen, what pattern do you see in the number of triangles that are
So it's 2 minus the number of sides.
2 minus the number of sides?
And minus
2 minus the number of
And
sides?
minus.
The
minus
number of
2.
sides minus 2, right?
Minus 2.
And that is actually the case. If you can kind of see it visually too, can't you? If you are drawing lines from one point, you can connect to all the points except for the ones immediately next to them, right? So you know that it's going to split into 3 triangles for a hexagon, or pentagon, and 4 for a hexagon. That means since each triangle has a sum of interior angle measures as 180, it'd be 180 times n minus 2. Guys, this is really powerful because no matter whether it is regular or irregular, whether it has 10 sides or 100 sides, you can figure out the sum of the interior angle measures. Even better, if it's regular, right? If you know it's a regular decagon, you can figure out not only the sum, but if you divide it by 10 angles, you can figure out what each one is in terms of their measure. The Polygon Angle sum theorem. The sum of the interior angles of a convex polygon with n sides is n minus 2 times 180. So if it's a pentagon, that means it's going to have n minus 2, so 8 triangles. And 180 times 8 is the sum of the interior angle measures. What is that?
1440.
Yes. Oh, you guys are fast. 1440 degrees altogether, which means if it were a regular polygon, each angle will have the measure of angle as 144, right? Each angle will have the measure of 144. So let's practice after the break. For now, you guys can take a break and we'll come back. All right, so let's do the first one together. We're finding the sum of the interior angles of a heptagon. How many sides does a heptagon have again? 7, right? It's a 7-gon. That means how many triangles can a heptagon have that covers all the interior angles? 5, n minus 2, right? So 5 triangles, which means the sum will be 180 times 5. What's 180 times 5? 900. Yes, 900 degrees will be the sum of the interior angles of a heptagon. Take some time to figure out these two. Think carefully about the second one here. Exterior angle, if you want a reminder, is if this is the interior angle, this is the exterior angle. Right? So if you know the interior angle, the exterior angles are the supplementary angles. What's so funny? What's so funny? Yeah. Didn't this happen last week too? You guys just started laughing. I have no idea. All right, anyway, figure this out. We have a regular 13 gone. First figure out what the interior angles are, and then figure out what the exterior angles then must be. What's the measure of each interior angles, guys? Dante?
Interior?
Mm-hmm.
1,980 over 13.
What's that?
1,980 over 13.
Right, which is about 152. Okay? Which means the exterior angles must be
It should be 230. 208.
28, right? They have to add to 180,
Yeah.
right? So you first find the sum of the interior angle measures for the entire polygon divided by 13 because it's a regular 13 gon, which gets you the measure of each interior angle, and then find the supplement, which is about 28 degrees. Yes?
And so then total would be 364.
If you were to add all the exterior angles, something like that. We'll talk about that after. That'd be good. Let's do this one together. Find the measure of each interior angle of this figure. What kind of polygon is this? It's a hexagon, good. It's convex, and it is not regular. But we do know the sum of the interior angle measures for a hexagon. What is that? We did this one 2 slides ago.
It's
720 has 6 sides, which means you have to multiply 180 by 6 minus 2, or 4, which is equal to 720. Which means this x plus 22, this one, these two angles, plus 90, plus x plus 22, and plus 90 must equal 720. But let's just work smart, not. I mean, you should work hard too, but let's just work smart here. We see that this is a mirror image, right? Well, not mirror image. We know that they repeat, which means they should. If you just add one set of them, it should equal 360, right? So that means 2x plus 22, if you add like terms here, plus 90 must be 360. Let's subtract 22 and 90 from both sides, which is 112. If you subtract it from 360, that's 248, which is 2x. This must be 124 degrees. That means x over there on the left corner is 124. The one next to it is 146, 90, 146, 124, and so on. Yes?
I did it like this. I did 4x plus 44 plus 180 equals 720. Then I did subtract 180 from 720, got 540, and then subtract 44 from.
Yes. And then that equaled 4x, right?
Yeah.
Yeah. So 4x equals 496 was what you should have.
Oh yeah, I think it's something.
Subtractions can get away sometimes. So yeah, if you divide both sides by 4, you get x equals 124. Good. All right, let's talk about exterior. I wish I had a blank slide before this so we can talk about this a little bit, but this is a really cool theorem. The sum of the exterior angle measures, one angle at each vertex, of a convex polygon is 360. Do you believe it? Is it true?
Yes.
If it's on the slides, it must be, right? So let's think about a triangle. Actually, let's think about a. I don't know why I can't erase it. It's so weird. Anyway, let's think about a equilateral triangle. Let's see if that works, or equiangular in this case. Doesn't really matter which order you draw the exterior angles, as long as you form a linear pair with it. So if you have 60 each, because it's an equiangular triangle, that means each exterior angle, one at each vertex, must be 120 degrees. And altogether, they add up to 360. Let's see if it's true for rectangles. Yes, because then we have 4 right angles that add up to 360. Could this be true for all polygons? It, in fact, is true. I wonder if I can do zoom out here. Can I do zoom out here? Oh, I can. Let's see, can I zoom in? All right, I can zoom in. All right, so I'm gonna try this one thing. Let's see if it works. Oh no. I'm totally messing this up. Shoot. Alright, everyone just look for now, okay? If you have let's see. How do I explain this? I need notability for this. Never mind. If you were to look at a polygon, say let's do some quadrilateral here, and we draw exterior angles. This angle over here, the same as this angle, right? Like it's the same angle, right? That's like maybe like 50 degrees, 50 degrees, 50 degrees. Check this out. That's one exterior angle. This is another exterior angle. This is another exterior angle. And this is another exterior angle. The sum of the exterior angles is 360. Which is really cool. But think about, I mean, you can say this given that given that if you go around the circle it's 360 degrees. But think about this circle as the infinity gone again. Okay? Like, I mean, we won't call it infinity gone, but think about it like that. It has infinite number of it has infinite number of interior angles. That's huge. Infinite number of exterior angles. That's tiny because interior angles are big. So the exterior angles must be super small. But all those infinite number of angles combined is 360. I know. It's like stressful almost. Yes?
So say if we were to draw like an octagon, all the exterior angles of an octagon would equal 360.
Yes, for any polygon, if you add up the exterior angles, that would be 360.
I thought a circle wasn't a polygon.
It's not.
But
if you were to consider it as like infinite sides, infinite sided polygon, even that would work. And you see that, oh, it's 360 degrees. It's pretty cool, pretty cool. I know, it is crazy. It is crazy. So if you think about a regular hexagon here, before learning about the exterior angles, you will have to figure out the measure of each interior angles, right? And then subtract and find this supplement. But now it's even easier than that because you know this has 6 sides. So if all the interior angles, if all the exterior angle measures have to add up to 360, if this is regular, which means these are all equiangular, how big is each exterior angle?
I have Y.
Y?
Wait, which one are we talking about?
Over here. First one.
I have one.
Okay. What about the first one? How big, or what's the measure of each exterior angle if all the exterior angles have to add up to 360?
360 divided by 6.
Right? If these all add up to 360 and they're all congruent because it's an equiangular polygon, then it's 360 divided by 6. That means each one is 60 degrees big, or each one has a measure of 60 degrees. This might be actually easier. I think this is easier than finding the measure of each interior angle of a polygon. We can just find the supplement of this one instead of having to do n minus 2 multiplied by 180 divided by n, right? It's easier for you to actually find the measure of the exterior angle and find the supplement. We can apply the same concept to the value of y here. Remember, all those have to add to 360. So 4y plus 2y plus 6y plus 4y must equal 360. How many y's do we have there? 16 y's. Which means each y is
60 degrees.
not quite. What's y in this case? Yes. 22.5 degrees. Oh no, not degrees, sorry. It's just 22.5 is y. And then if you plug that in, that means measure of k, or this angle over here with 2y must be 45 degrees. This must be 90 degrees, and here is 112.5. No, sorry. Be 135. Okay, if you multiply 22.5 times 6. So let's recap really quick. We have Polygon interior angle sum theorem, which says n minus 2, given that this is the number of sides, times 180 equals a sum of interior angle measures, right? N minus 2 here is a number of triangles that you can form. Why is it important to form these triangles inside of a polygon? Why? Why do we care about the number of triangles over there? Triangles are cool. Jonathan?
Because then you can bring the interior angles.
Yes, interior angles of the triangles make up the interior angles of the polygons. Yes. And the sum of exterior angle measures is a little simpler than that one. 360. Yes. So using those two, you can figure out the measures of interior angles and exterior angles. All right? Good stuff. So you see homework on Shobi. Make sure you study for the quiz of the theorems. That's from 6.2 through 6.5. And the three definitions.